Welcome to your second part of your final lecture. In this part, we are going to discuss the communication security after we have covered information security in the first part of the lecture. We will go through IPsec, firewalls, virtual private networks, and wireless security. As we have said earlier, security wasn't the main concern when internet has started, but it has become very important as internet became widely spread. Internet Engineering Task Force has known for years that security was lacking in the internet. So there was a debate on where to place security. If it was placed in application layer, it would be a total solution, but many applications will be in need to be rewritten. In transport layer, it will help the unaware users to some extent, but it won't provide total security. The discussion ended with creating a framework known as IP security, IPsec, that is implemented in the network layer. IPsec is a complete framework for multiple services, algorithms, and granularities. Multiple services because not everyone wants to pay price for having all services at the same time. That's why services are optional. Multiple algorithms, it's a framework and it needs to survive. Even some algorithms were broken later. Multiple granularities, because it makes it possible to protect single TCP connection, all traffic between pair of hosts, all traffic between pair of secure routers, and other possibilities. IPsec is connection-oriented. A connection in the context of IPsec is called Security Association and SA. SA is simplex connection. In case you want to connect two entities in duplex connection, you should have two simplex connection, one in each direction. SA has an identifier associated with it. It defines it uniquely in the context of the connection. Security identifiers are carried in packets traveling from secure connections and are used to look up keys and other relevant information where secure packets arrived. IPsec has two parts: to establish keys, Internet Security Association and Key Management Protocol, and to describe two new headers, authentication header and encapsulation header. IPsec has two modes, transport mode and tunnel mode. In transport mode, IPsec header is inserted just after the IP header before the TCP header. IPsec header contains security information, primary, the SA identifier, new sequence number, and possible integrity checks for the payload. In tunnel mode, the IP packet and header are encapsulated in the body of a new IP header and completely hidden. IPsec authentication header is inserted directly after the IP header before the TCP header. It has 32 bits word size and it has multiple fields. The next header field is to store the previous value of the IP protocol field before it has been set to 51 to indicate an authentication header. The payload length is the number of 32 bits words in authentication header minus 2. The security parameter index or the security association is the connection identifier. The sequence number to number all packets sent in a certain security association. Authentication header contains the payload signature, hash signature with hash message in authentication code, for example. Authentication header is useful when integrity check is needed, but not secrecy. While the ESP header, the encapsulation security payload header, it works in both transport mode and tunnel mode. In transport mode, it's inserted directly after the IP header before the TCP header, and the ESP header, the TCP header, the payload and padding are all authenticated, while the TCP header and the payload are encrypted. In tunnel mode, the ESP header is inserted directly after the new IP header, before the old IP header, and all the fields from the ESP header up to the payload are authenticated, and from the old IP header to the end of the payload are encrypted. The question here, which is better to use, authentication header or encapsulation header? Originally, authentication headers handled only integrity, encapsulation headers handled only secrecy. Now, ESPs has both integrity and secrecy, but majority of products supports AH because it's easier to export it from USA without having secrecy. What is seen in the future is AH is likely to be phased out and ASP is to take. IPsec provides secure transition for the data but does not provide securing your network. To connect your computer to be able to log in anything, anywhere, anytime is for individuals at home is wandering around the internet is a lot of fun. For corporate security managers, it's a nightmare. Some information might leak out, some information might leak in. So IPsec, as we said, is good for protecting data in transit. Something is required for disallowing data from transfer. Here comes firewalls. Firewall is a device that protects your internal network from the outside world by regulating the traffic from inside to outside and from outside to inside. Here is the setting where we have a single firewall protecting the internal network and a router connecting to the internet. In the middle is what we call demilitarized zone, and this is a zone where we set up our services that are required to be available to the outside world, such as web server and email server, while other servers like database server or file server are kept behind the firewall. Firewalls comes in different forms, so a company must find the solution that meets their unique networking needs. We can define them, can divide them according to delivery. That refers to where the firewalls operate in the network context. Delivery options can include hardware and software, cloud or cloud-based systems. Technology, this refers to how firewall actually works. Firewalls technology includes packet inspection, filtering, proxy or app-based filtering, and stateful firewalls. Packet filter routers are typically driven by tables configured by system administrators. The system administrator set a list of sources and destinations that are acceptable or that are blocked, and set default rules about what to do with packets coming from or going to other machines. While the application gateways or proxy routers inspect header fields, message size, and contents. The packet filters are better to be set inside and outside. Inside to check outgoing packets, inside to check incoming packets, and in the middle, an application gateway will be useful for further examination for the packets. Even if the firewall is perfectly configured, plenty of issues will still exist. An intruder outside the firewall can put false source address to bypass the check, which is called IP spoofing. The insider can encrypt or even photograph documents and ship them outside. Attacks like denial of service and distributed denial of service attacks cannot be actually prevented by a firewall. Denial of service attacks happens when a server is overwhelmed by a lot of requests, so it's unresponsive. There are two types of denial of service attack: distributed denial of service attack and denial of service attack. Denial of service attack has less traffic because it's launched from a single computer that sends a lot of sync requests to the web server without without applying acknowledgements to the server. So the server will be opening a huge amount of connections that are not complete, and the server will be unresponsive. Well, distributed denial of service attack, on the other hand, happens from multiple computers run by a single server, where the attacker infects multiple computers, turning them to botnets and using them to launch his attack. The amount of traffic in the denial of service attack is less than the amount of traffic in distributed denial of service attack. This is from single computer, this is from multiple computers. The execution method for the DOS, it's carried by a tool or a script on the attacker's computer. Here is carried by botnets, making a botnets network. The source is easier to discover, and it's easier to terminate the connection that is causing the problem. Here the source is not easy to discover because it hides itself behind multiple computers, and it's not easy to disconnect all attacking computers. The third technology we're going to discuss today in connection security is VPNs, virtual private networks. A virtual private network is a private computer network that functions over the top of a public network, such as the internet, and usually utilize data encryption and encapsulation to provide secure access to the company's network or to a private server. VPNs use tunnels to secure data by encrypting the data that is being transferred through the tunnel and encapsulate it. The tunnels create a private pathway shielding transmitted information from inspection and interception and authorized access. Encryption algorithms cover data into unreadable code during the transient, ensuring even if the data was intercepted, it remains inaccessible and secure. As you can see here, the tunnel is a virtual connection across the internet between two routers that are VPN-enabled routers. A virtual private network uses tunneling, can connect users while traveling to the main office, or home user to the main office, or two offices, two branches together. This is how it looks using tunnels. The users are not aware of the existing of the tunnels at all. To them, as if they have a leased line between their computers and the network. VPNs in the past were implemented in frame relay and ATM over the internet. Nowadays, they are implemented using firewalls and IPsec to encapsulate the data. As we have stated before, wireless networks are completely different than wired networks. That's why wireless security is discussed separately in this lecture. We will discuss two topics: 802.11 security, wired equivalent privacy, and Wi-Fi protected access to, and Bluetooth security. Web or wireless equivalent privacy encrypts traffic using 64 or 128 bits key in hexadecimal. It's a static key, which means all the traffic, regardless of the device, is encrypted using the same key. Web key allows the computers on a network to exchange encoded messages while hiding the message contents from intruders. The key is what is used to connect wireless security-enabled network. Breaking web was easy. The key was the single point of failure. IEEE stated that they knew that web was not secure enough, but it's better than no security. And users should have used other forms of security like transport layer security. And they promised that the next version, 802.11i, will have better security. So they came WPA2, Wi-Fi Protected Access 2. It prescribes a data link level security protocol for preventing wireless nodes from reading or interfering with messages sent between other pair of wireless nodes. It also goes by the trade name WAB2. There are two common scenarios for WAB2. The first is a corporate setting where the company has a separate authentication server that has username and password database and can be used to determine if the wireless client is allowed to access the network or not. While the second scenario is in a home setting where there is a single password used by all users to connect with the wireless router. Bluetooth security, on the other hand, has three modes, ranging from no security at all to fully encryption and data integrity control. No security is like locking the barn door after the horse has escaped. That means implementing security after no security after something happened is just like locking the barn door after the horse has escaped. Physical security with frequency hopping, which is not very secure, and it has pass keys to checking for pass keys, selecting random 128-bit session key for encryption using stream cipher called E0, and integrity control uses SAFER+. In the following part of our lecture, we'll discuss application security, starting with email security. The first attempt to secure emails was Pretty Good Privacy by Philip Zimmermann. Pretty Good Privacy is a complete package that provides privacy, authentication, digital signature, and compression, all in easy-use form. Released in 1991. It encrypts. The encryption is done by international data encryption algorithm. The key management is done by RSA, and the data integrity uses MD5. The process is simple and straightforward. The original plain text is hashed by MD5. Then it runs through RSA. Then it's concentrated with the signed, the plain text is concentrated with the hashed signed plain text. Then all is compressed using zip. And then all after the compressed plain text is run through IDEA to have a ciphertext along with the key that is encrypted using RSA. All are concentrated together, run through base64 encoder to generate ASCII code stream to the other network. Pretty Good Privacy message consists of header and message body payload. The header has multiple fields, ID of the receiver, the master key for encryption, signature header, timestamp, ID of encryption key of the sender, types, MD5 hash function, message header, and file name, another timestamp. The master key is encrypted using the receiver's encryption key, and the MD5 hash is encrypted using the sender's private key. All the fields from the signature header to the end of the payload are encrypted using IDEA, and all the message from the ID of the receiver to the end of the message is encoded using base 64 encoding. Another approach for email privacy was Privacy Enhanced Email Standard, developed in the late 1980s, and it was an official internet standard. It is described in RFCs 1421 to 1423. PAM is long gone. It's not used anymore because it has key management problem. Its president was S-MIME, Secure MIME, and it's described in RFCs 2632 to 2643. Secure MIME provides authentication, data integrity, secrecy, and non-repudiation. It's also quite flexible, supports a variety of cryptographic algorithms. It has variety of new MIME headers, and it does not have rigid certification hierarchy, beginning at a single root, as the problem was privacy enhanced email before. Instead, it has multiple trust anchors. Our next topic is web security, where we'll look at the threats, the secure naming, SSL, and mobile code security. Hackers versus crackers. Hackers are the serious attackers that attacks sensitive systems like banking system, military systems, industrial systems to gain secret information to benefit from it. While crackers are amateur attackers, like the ones that we're going to have examples about now. In 1999, a Swedish cracker broke into Microsoft Hotmail website, created a mirror website where everyone can read the emails of everyone. A 19-year-old Russian cracker named Maxim broke into an e-commerce website, stole 300,000 credit card numbers, and asked them for $100,000 to keep these numbers secret. They refused to pay him, and he actually published the numbers. A 23-year-old California student emailed a press release to a news agency falsely stating that XML Corporation was going to post large quarterly loss, and the CEO was resigning immediately, causing a huge drop in the stock market value of the corporation. To provide security on the application layer, many techniques and technologies are used, as we have seen in email security. The next step is secure naming. That means to secure DNS systems so that they won't be hacked. For example, if the DNS was actually hacked, if Alice wants to get Bob's IP address and Trudy has hacked the DNS server, then she will simply ask the DNS server for Bob's IP address and gets through the IP address instead and be communicating through this web server rather than Bob's web server, assuming that she's actually talking to Bob. Trudy, to do this, have to do a lot. It's not an easy task. She has to guess the sequence number of the server by sending the server lookup requests for her own IP address, and then use this sequence number once she gets to ask for Bob's address number and replies using this sequence number before the DNS internet, the root DNS sends back the reply. For secure DNS to happen, it's based on public key cryptography, where each DNS zone has public-private key pair, and information is sent to the server signed with the originating zone's private key. So it's decrypted by its public key, and that's how the receiver will verify the authenticity of the message. Secure DNS or DNS security offers three fundamental services: proof of where the data is originated, public key distribution, and transaction request authentication. DNS records are grouped into sets called RR sets. An RR set may contain multiple records. Each RR set is encrypted and hashed, and hash signed by the Zoom private key using RSA, for example. Upon receiving the signed RR set, the client verifies whether it was signed by the private key of the originating zone or not. An example for an RR set here, where there are three RRs, resource records, bob.com, time to live, class, type A, that means this is the IP address of Bob, if we remember. Then bob.com, time to live, class internet, this is Bob's public key, and bob.com, class internet, this is the signature, the hash signature of the DNS of the zone. The next technology we're going to discuss is Secure Socket Layer, SSL. SSL is an encryption-based internet security protocol. It was first developed by Netscape in 1995 for the purpose of ensuring privacy, authentication, and data integrity in internet communication. SSL is now followed by TLS, Transport Layer Security, and it's more used in nowadays encryption more than SSL, but they are both coexist. A website implementing SSL or TLS has the HTTPS rather than HTTP, indicating secure HTTP. The protocol stack for SSL looks like the following: application layer with HTTP, security layer with SSL, transport layer with TCP, network layer with IP, data link layer with point-to-point protocol, physical layer that can be modem, ADSL, or cable TV, or whatever physical connection is there. As you can see, there is a layer inserted between the application layer and the transport layer for security. SSL connection starts with the client messaging the server to initiate SSL TLS communication. The server will send back an encrypted public key certificate. The client will check the certificate of the server and sends an encrypted key back to the server. The server will encrypt the messages with the encryption key sent by the client and send it back. Hence, there will be a secure connection between the server and the client. SSL, the messages between the server and the client, the client, Alice, is connecting the server, Bob, sending SSL version that she is using and her preferences in the communication and her public key. Bob sends back the SSL version it's using, the choices from the preferences, and its public key. It will set also a chain of X509 certifications to prove that the certificate he has sent is actually authentic. Now the server is done. The client will send a pre-master key to the server. The server will change the cipher, and the client is finished. Then the server will change the cipher, and the connection is now established. The data transmission in SSL happens first in the application layer, where the message from the browser came. It is fragmented into two parts. Each part is compressed, and a message authenticating code header is added. Then the whole message with the header is encrypted, and all is encapsulated, adding an SSL header to it. Our last application layer security topic will be mobile code security. Web pages often contain small programs including Java applets, ActiveX controls, and JavaScripts. These are called mobile codes. And downloading and executing these mobile codes is obviously a massive security risk because you don't know what is the origin of these codes, whether they were safe enough to be executed on your computer, whether they have hidden agenda or not. Java applets are small programs written in Java, executed in Java Virtual Machine, as we have discussed before. Java applets can be trusted if they're coming from the local disk, for example, or not trusted if they're coming over the internet. If they're trusted, they will be executed directly without any question. If not trusted, they will be actually placed in what we call a sandbox to restrict the behavior and trap the attempts to use the system calls, the system resources. If an applet tries to use a system resource, the call it made will be passed to security monitor to approve. If it wasn't approved, it will be rejected. If it was okay, it will be executed. As we can see here, we have two types of Java applets: trusted Java applets and untrusted Java applets. The trusted Java applets is run directly on the Java virtual machine, and the untrusted Java applets has a sandbox containing them, restricting their execution. ActiveX controls has different attempt for security. It comes with a digital signature hashed of the code and signed by the creator using public key encryption. This is called code signing. When ActiveX control shows up, the browser first verifies the signature and makes sure it has not been tampered with. If the signature is correct, the browser then checks if the internal tables say that the program creator is trusted. If not, it will check the chain of trust back to the trusted creator. If the creator is trusted, the program is executed, otherwise it will not. Microsoft's system for verifying ActiveX control is called Authenticode. JavaScript, on the other hand, despite it has a long history of leaky implementations, it doesn't have formal security model. Each vendor handles security in a different way. Browser extensions, add-ons, and plugins are another form of mobile code. These are computer programs to extend the functionality of a web browser. Plugin often provides capability to interpret or display certain types of content such as PDFs or Flash animation. Extensions and add-ons provide new browser features such as better password management. Add-ons and plugins should only be installed if they are from trusted vendors. Malware is another form of mobile code. People might not really want to download it into their computers because it will cause serious harm, but they do. Either they are tricked into doing it, or they downloaded a program that looks innocent but actually has another purpose behind the scenes. There are multiple types of malware, that's malicious software, such as computer virus, which is a type of computer program that attaches itself to other programs or files. When executed, it writes its own code so it can spread itself from one program to another, leaving infections as it travels, just like the human virus. A computer worm is a type of malware whose primary function is self-replicate and to infect other computers who are remaining active on the infected systems, replicating itself more and more, crippling the system that it exists on. A Trojan horse is a type of malware that once downloaded into the computer looks like it has some function, some legitimate function, while behind the scenes it has a different function such as working as a spyware, collecting information, or turning your computer into a bot. Your last reading assignment is section 8.4 and 8.7, chapter 8, Computer Networks, under Stuart Tannenbaum, and chapter 52 from Internet Working Handbook by Cisco Press. No writing assignment. Wish you all the best in your exams. Your questions are most welcome in your Telegram group and or in private. Best of luck.